When we covered straight lines, one of the key things we looked at was collinearity of points. Now that was, were points lying on the straight line, how could we prove they were, and actions we could take when they were, i.e. finding parts of coordinates. What we're going to do is take that two-dimensional representation of it now and stretch it into 3D. We're going to look at what happens if we have a three-dimensional system. How do we show that points are collinear? Now think back to when we did it with straight lines. There was a couple of key things we had to show. For any set of 3 points, we had to show firstly that the same gradient existed between pairs of points, and secondly that there was a common point shared between both of those. So if I had the points A, B and C, I would have to show that the gradient from A to B matched the gradient from A to C or the gradient from B to C. What I would then have to do is take any pair of these and show that because the gradients matched and they shared the same point, i.e. this one here would share A between A and B and AC, or B between BC and AB, or AC and BC, there's always a common point there. If we could show that and show the same gradient, one, the same gradient meant they were parallel, but two, because they had a common point instead of being parallel to each other, they were parallel and shared that point. So then they were all collinear. But the question is, how do we extend this into 3 dimensions? We've got another dimension to worry about. It's not just a nice flat surface and a flat plane. How do we bring this third dimension into play? So imagine I've got 3 points, A, B and C here, and it's in a 3-dimensional system like this. Now if you think about what we did before, we'd have to show the gradient of sets of points were parallel. So if this was 2D, I'd have to take these 2 points and show the gradient there was equal to the gradient there, so they were parallel. The same logic for that applies in 3 dimensions. We're just extending it. If I've got 3 points and the gradient from here to here is the same as the gradient from here to here, they're parallel within that system. So they're parallel within this entire 3-dimensional system. And the same logic applies with a common point. If I show that AB has the same gradient as BC, they're parallel, yes, but because they have a common point, not only are they parallel, they're parallel through that point, which means the 3 points are collinear. So it's the same logic and the same general idea behind it as if we had just 2 points in a 2-dimensional system. For 3D, what that means is we have to get the vectors AB, BC and AC. We need a pair of them to be parallel. So we take any pair of those vectors and show that they're parallel. And they must also share a common point. So I could pick AB and BC as my pair, I could pick AB and AC as my pair, or I could pick BC and AC as my pair. It doesn't matter which pair, as long as there's a common point. Now remember, for parallel vectors, if one vector is a multiple, let's say 2, of the other vector, that means their base vector is the same, so they are parallel. So for example, if I had the vector 1, 1, 0, and I had B being the vector 2, 2, 0, what that means is this vector can be written as 2 times 1, 1, 0. So these two have the same base vector here, it's just multiples of each other, so they are parallel. They also share a common point, so if I let A represent my AB and my B represent the BC, they would share B as a common point, so they're all collinear. Let's have a look at how this works. Now imagine I've got 3 points, A, B and C, and the question is, are the 3 points collinear? Well, we have to think of the logic. So we have to think, right, take a pair of vectors, AB, BC or AC, make sure they've got a common point, calculate them and determine if they are parallel. If they're parallel, they're all collinear as long as they share that common point. So let's take the vector AB. So the vector AB is equal to the B minus A vector. Now B and A are just the position vector of the point A and the point B. But remember, because these are the position vectors with relation to the origin, the values here give you the vector you're after. So for B, it would be 3, 1, 3 as a column vector. And for A, it would be negative 1, 3, 5 as a column vector. Perform the operation, 3 take away negative 1, that gives you 4. 1 minus 3 is negative 2. 3 minus 5 is negative 2. So there's my vector AB. I could do the same for my vector BC. So in this case it would be C take away the B, My C vector would be given by the point there, so 5, 0, 2. Take away the B, which is 3, 1, 3. That would then give me 5 minus 3, which is 2, 0 minus 1, which is negative 1, 2 minus 3, which is negative 1. So I've got the vector 2, negative 1, negative 1. I could also do the vector AC, and I'll show you that for completeness, which would be given by C take away the A vector. Now C minus A is the 5, 0, 2, take away the position vector for A, which is this one, so take away negative 1, 3, 5. So 5 minus minus 1, that ends up giving you 6. 0 take away 3 gives you negative 3. 2 take away 5 gives you negative 3. Now, if we look at each of these, what you'll notice is that this vector here is equal to twice the BC vector. This vector here is equal to 3 times the BC vector. So what that means is both of these vectors are just stretched out scalar multiples of this one. So i.e. if my BC vector went from there to there, my AB vector would just simply be pointing in the same direction, but a little bit further, and my AC would then go even further because it's a multiple of 3 times bigger. So what this means is they're parallel to each other. So these vectors are all parallel, and if I pick the pair AB and BC, they share the common point of B. So what I could then say is since AB is equal to twice the BC, what that means is they're parallel. Because they're parallel and share a common point of B, so B equals a common point, what I can then say is therefore all 3 points A, B and C are collinear. They have this parallel gradient, they're parallel vectors, they share a common point. That's how we prove that they're collinear. Here's another example for you. Imagine I've got the points A, B and C given by this, and I'm again asked, are A, B and C collinear? Again, same logic. Pick 2 pairs of vectors, make sure there's a common point between them. If they're multiples of each other, great. If they're not, then they are not collinear. So let's do A to B, which again is given by the B take away the A. So in this case, it's given by the 9, 2, 0, take away the 0, 5, 1. So 9, 2, 0, take away that. 9 minus 0 is just 9. 2 minus 5 is negative 3. 0 minus 1 is negative 1. So that's my AB vector. My BC vector is given by C take away the B. So in this case, that's negative 1 minus 6 minus 2. Take away the B, which is 9, 2, 0. Negative 1 minus 9, so that gives me negative 10. Negative 6 minus 2 gives me negative 8, and then minus 2 there. Now, this one here is not a scalar multiple of that, and vice versa. What I can then say is, therefore, AB does not equal NBC, so a scalar multiple of BC. Simply, therefore, they're not collinear. So all 3 points in this system do not lie on the same line. They didn't follow the rule of parallel vectors with a common point. They're not collinear. Like I said, very, very much the same as with a straight line with points in 2 dimensions. The only difference being we've extrapolated out that 3rd dimension to give it a little bit more, let's say, 3D realism. And that's how we do it. Same idea. Parallel vectors, common point, we're right there.